Hi everybody, this is week 3. Notice I am now in a fancy looking server room to symbolize the fact that this is the week where we start kind of working with some more realistic data. Before we do that though, I want to do two things this week. One is to introduce a little bit more Python for reading files and for graphing and visualizing data. That's going to be in the sort of the second part. If we had a live class, that would be the second class of the week. But in this video, I want to do the first class of the week, which is I want to introduce to you guys the machine learning task, specifically the task of supervised classification. And normally I would do this through what I would call some unplugged activities. So I'm going to present those activities to you. These are paper and pencil exercises that I've used several times and which I think really help to help you to understand what the machine learning task is for supervised classification, how it works, and we can also draw out some interesting and important lessons and introduce a few basic concepts. So we're still not going to do any machine learning this week for real. We're going to kind of simulate it. Now, if you look at the materials for this week, by the time you see this, there'll be some videos and stuff here. But under materials, there's two things here, supervised classification and debrief. Normally I would put students into groups and we would try the two different activities in supervised classification activities, and then one by one I would debrief them with the debrief. Now everything is completely available here. You don't actually, I can't force you to do the activities. Well, I couldn't force you if you were actually in the class, but I can definitely put a lot of moral pressure on you to do them. But I think you should try at least one of them. So let me show you what the activities are, and then I will invite you to try them, and then in the second part of the video I will talk about the activities and sort of debrief them a little bit. So so the title of the thing here is ML Unplugged. And let me start by explaining to you what the supervised classification task is. So there are a number of different machine learning tasks, but by far the most common and the most well understood one is called supervised classification. It's classification, which means it's about putting labels on things. This is a picture of a cat. This is not a picture of a cat. This is a document about the economy. This is a document about politics. We're trying to categorize things. This is a lot of the data that we'll look at will be medical data. So in some cases they will be imaging data from evaluating potential tumors in a patient. So you might want you would want to categorize this is a malignant tumor, this is not a malignant tumor. So that's the classification task there. So that's what it means to classify. Supervised means that there is a training phase. So we train the machine learning algorithm. There are unsupervised algorithms that kind of train themselves, but in supervised classification we train the algorithm, and we do it by taking a portion of our data and calling that the training data. So if it's images, it's a set of encoded images with the labels attached, saying whether it's a cat or not. If it's medical data, it's going to be a set of numerical readings from an imaging system that's with the correct classification of whether it's benign or malignant. So that's the training data, and we give the training data to the algorithm with the labels attached, and it uses that to form a theory of what separates cats from non-cats, politics from the economy, malignant from non-malignant. So it forms a theory of some kind. And the type of theory that it forms is sort of the defining point for each of the machine learning algorithms we're going to look at. They each approach this task in a different way. Then typically we will, when it's trained correctly, we'll send it out into the world and it will look at pictures and news articles and scanner data from medical scanners that it's never seen before, and hopefully if it learned a good theory it will be able to categorize them with some degree of accuracy. So when we're experimenting and training algorithms, we usually have a training data set and then we have a testing data set, and we know the answers for both of these sets of data, but we only tell the system the answer for the training data. So it gets training data with answers attached, it learns its theory, then we give it the testing data without telling it the answers. We see what it predicts, and then we see how well it did compared to what we know are the correct answers. Okay, the models are all kinds of things. They could be a model of the task, could be an equation, could be a set of rules, We'll look at decision trees, and there are lots of other ways. When it's ready, we test it to see how well it generalizes. So what I want you to do is I want you to be a machine learning algorithm. And if you've got a group of people you can work with, it'd be great to pause after I've introduced this task and try the task yourself with a group of people. This is the training data. You might, if you've ever played the game SET, S-E-T, then you recognize this. I took the symbols from that game, but we're not playing SET, okay? So forget what you know about SET. This is a different game that we're playing here. You can see here there are a number of examples of symbol sets, and there are two classifications. So the first one is classified as out, and this one is in. So some of these things are the things we're interested in. They're the types of symbol sets that we like. Those are the in ones, and the ones that we're not interested in are the ones labeled out. So your job, or your group's job, is to just take a look at all these and try to come up with a theory of why something's in versus out. Okay, so, and it can take, I don't want to say too much to prejudice you about the type of theory you create. It can be any kind of theory. It can use any aspect of the training data. Don't use these numbers though. These are just numbers so that we can talk about the training data. They're not part of the set. So yeah, that's your training data there. And what you're trying to do is come up with a theory. Now there is a correct theory in this case. There is a theory, or there may be a couple of theories that get every item correct, but don't obsess over that, okay? If there's 15 examples here, if you have a theory that gets 12 or 13 or even 10 or 11 correct, that might be a pretty good theory, okay? So don't go nuts trying to figure out the exact theory. It's pretty hard to do. I don't think anybody's ever done it in any of the classes I've taught. But try to get one that gets them pretty correct. Okay. When you're done that, when you've got your theory, I want you to come over here. Hang on, let me just get rid of this. There we go. I want you to come over here to the testing data. So you are the machine learning algorithm. I know the correct answers to the testing data, but you don't. So then you take your theory and just apply it to each of these examples and categorize each example as either in or out. Just you can print this out and write them on there, or you can scribble it on a piece of paper, or however you want to do it. And then in the debrief document, you can see how many you got right, how many your algorithm got right. There is a second task as well. So normally in class, we would do the first task, and then I would debrief it, and we would do the second task. I'm just going to introduce both tasks, and then after that, I'll debrief them. And I'll leave it up to you how you deal with it. But you could pause at this point and try the task. I would normally give the class maybe 15-20 minutes. People tend to take a long time with this one. Maybe give yourself 10 or 15 minutes if you're doing this one, and then call it a day and just go with whatever theory you have and see what the classifications are for these unseen data sets. The second task, this is more realistic data. This comes from a real data set where the red points here represent counterfeit banknotes. So these are like dollar bills. This is American data, I think, so it's probably like $50 bills or $100 bills. They put them under scanners and then they analyzed them and they pulled out 4 features. Here they are. So they analyzed the images for, I don't know what all these things mean. I'm not an image processing guy, but they pulled out the variance, the skewness, the kurtosis, and the entropy of the image. So the full data set has 4 values for each banknote. I'm just showing you 2 here so that we can visualize it. And we will do this a lot. We will take multidimensional data and project it onto 2 dimensions like this to try and get a sense of the shape of our data. So I've just used skewness and variance here. So your hands are a little tied here because you don't have all the information. But again, what I want you to do is come up with a theory that's going to essentially separate red from green. So a theory that separates the counterfeit from the non-counterfeit. And you can already see this is real world messy data. You can already see there's some overlap here. It's going to be really hard on the training set to get 100% accurate, but that's not really your goal. Your goal is to get a pretty, and it's almost never our goal in machine learning to try to be 100% accurate for reasons I'll explain. So try to get it so that it's pretty accurate. Okay, so your task is to form a theory. It could be rules, equations, drawings, just an informal description. You can scribble on the picture if you want. Whatever form it takes, I don't mind, but write it down. Then you move on to the testing set. This will be a lot easier to work with if you've printed these 2 pages, because you can put them up next to each other to see where these points fall. But then your job then is to use your theory to label each of these points as counterfeit or legal. So those are the 2 classes, legal or counterfeit. Okay, so if you choose to do this one, usually this one doesn't usually take people as long. But once you've done that, once you've got your theory, label these points according to your theory. So you form the theory by looking at this, you label them here, and then we'll move on to the debrief. Okay, so here's where it would be great if you would stop the video and go and try one of these tasks, at least one of these tasks for 10 or 15 minutes, maybe with a partner or with a group, and then come back, restart the video. At that point, go to the debrief of activities handout and read over it, or listen to what I have to say in the video about the debrief. Okay, so I'm going to assume that you paused the video, and now we're back, and let's debrief this activity. So first of all, here's the solution for the first task. So for the sets of symbols, so this is, let's go back here, this is this task here. What I did was I put these symbols here, and then I created this if-then theory to generate the labels. So this is what I used to generate these in and out labels. So if the number of colors is 1, or if you have 2 shapes and they're both ovals, then it's in, otherwise it's out. So if you look at the ins, you see it's 2 shapes, both ovals, a single color, these are both a single color, this is a single color, and so on. That was the theory that I used to generate it. Don't freak out if it's not the same theory that you got. If you do use my theory though, if you do use this theory, then that makes these predictions for the 15 items in the testing set. So in the testing set here, these are the solutions. So at this point, what you should do is just pause for a second if you did this task and see how well did your theory do. How accurate was your theory on the training data, and how accurate was it on the testing data? So you may find there's a lot of different options. You may have only got 10 out of 15 on the training data, but you may do better on the testing data. And then think about the training data. Could it have been improved to help steer the learner towards the correct theory? So just do that for a second. I'll assume you paused, and we're back. Again, don't be upset if you don't get 15 out of 15. This is a super hard task, and B, you often don't want to get 15 out of 15 anyway. So let's talk about it. So first thing I want to talk about is the fact that, so in this case, the training data is consistent with multiple theories. It's usually better to have more training data. Here we had a tiny amount of training data, only 15 examples. Would have been great to have 100 examples, but that would be too much for a human being. And you need a wide and balanced variety of examples as well. So you don't just want all the examples are 2 ovals. That wouldn't be any good. Or all the examples only have 1 symbol. You want to make sure you have a wide, balanced training set when you're setting things up for your machine learner. And when 2 available theories seem just as good as one another, you need some way to choose between them. So here's a possible rule. It's an alternate match for the training data. So if the rule is if there's only 1 shape, then you're in. Otherwise, if there's 2 shapes and they're both ovals, then you're in. Otherwise, if there's purple anywhere, then you're out. Otherwise, you're in. So it's it's an else if chain of rules. So 1 shape is in. If that's not true, go to the next one. 2 shapes, both ovals? Yes, then in. If not, go to the next one. Is there purple? Yeah, if yes, then it's out. Otherwise, it's in. And I'll let you guys verify that, but anything with purple in it in the training data is, actually no, not anything with purple data, because it has to get through the whole list. So if it's got 1 shape, then it's in. So even if that shape is purple, then it's in. But if you carefully apply this rule, you'll see that it gets 100% on the training set, but it only gets 80% on the testing set. So this rule and my original rule are equally good at predicting the training set, but this one doesn't do as well on the testing set. So it doesn't generalize. It slightly overfits the training data. It gets too specific about, one shape, purple present, and so on. There's too much to it, and it misses the generalization that it needs, that if the number of colors is 1, then it's in. So that would have allowed it to get 100% on both the training and the testing set. So this is called overfitting right here, and it's an important concept and something that we're going to have to think about when we're looking at the performance of our algorithms. So here's an even more complicated rule. If there's one purple shape or one red shape or 2 oval or diamond shapes or 3 shapes that are all green or all red, then it's in, otherwise it's out. This also gets 100% on the data set, training data, but it does even worse. Oops, that should say on the testing data. I should fix that. I'll fix that before I post this stuff. It only scores 60% on the testing data. Now, what's our baseline here for performance on the testing data? Well, when there's 2 classes, if you guessed randomly, you should expect to get about 50%. So this rule does only a bit better than a coin flip, only a bit better than 50% on the training data. And here's a really extreme example. Here, I kind of broke the rule about using the numbers here, but you could write this out more fully. So what I've done here is I've just made a list of all the examples from the training data that are in, and I'm saying if it matches one of those examples, then it's in, otherwise it's out. That's also a perfect match for the training set. You might look at it and go, that's actually a pretty dumb rule. That's not likely to do well. It's really, really fitting. It's overfitting like crazy. It's fitting the specifics of the training data. It's not even trying to generalize about the number of shapes or the types of shapes or the shading or the colors. It's just saying if it matches one of these, it's in, otherwise it's out. And not surprisingly, it doesn't do very well. So there's nothing in the testing set that's an exact match for anything in the training set. So when it comes to examples it hasn't seen before, it fails badly. It categorizes everything as out, and it gets less than 50% correct. Okay, so in real-world tasks, you won't often get a problem like this where there is actually a correct solution that does 100% on the training and the testing. So because of that, you want to think about, how good do I want it to get on the training set? And what you'll notice here is that all these rules got 100% on the training set, but the more complicated they got, the worse they did on the testing data. So the more they overfit the training data, the more they underfit the testing data. So what you might often want to do is kind of choke back your machine learning algorithm. We're going to look at some algorithms that are perfectly capable of getting 100% on the training set, but they often come up with better rules if you clip their wings a little bit and tell them not to try and get 100% on the training set. Try to stop before you get to 100%. So here's a rule here. This underfits the training data. So it just says if the number of colors is 1, then it's in, otherwise it's out. It gets 87% correct on the training data, which for a real world task is really good. But it's worse than the other rules. But it scores 93% correct on the testing data, which is better than those other rules. So forget about the real rule for a second. Let's assume we didn't know that. We had rules 2 through 4 that got 100% on the training data and then fell over on the testing data and did terrible. And the testing data is what counts here because we want the machine learning system to be able to categorize new examples. This one does worse than those algorithms on the training data, but does better on the testing data. And so there's an important rule of thumb here for machine learning algorithms, which is that you don't necessarily want them. It's not like other computer science tasks, where you're looking for 100% accuracy. You are often not looking for 100% accuracy. You will often do better if you reel it in and get maybe 80% accuracy on the training data, then you'll do better on the unseen data. Okay, so if you've got a bunch of pictures of cats that you're giving the system, if it fits those pictures too exactly in its theory, then it will never see cats that look exactly like those pictures again when it's out in the wild categorizing cats, and it will not do well. By the way, that's an example that's for real. If you go, I don't know if you guys use Google Photos, but you can now search, and they have had a machine learner that has gone in and learned all kinds of categories. So, for example, I was about a year ago, I was looking for a photo of my grandfather. It was taken many decades ago, of a fox, him holding a fox. He had a pet fox. and I didn't know when I had gotten the photo, so I couldn't use the date to figure out where to get it. I just typed in Fox in the search bar, and to my surprise, it popped up that photo. So in the background, Google, it has a machine learner that is going through tons of labeled examples of photos and learning more and more and more categories, and then crawling through your photos and applying that data to them to be able to do that. I've also been able to find pictures of my grandparents that way, just by typing granny or granddad and finding those pictures. So pretty cool. Okay, so that's the big lesson there. There's some other stuff here on representation. The other thing that you have to think about in a task like task 1 is when you are, so we didn't have to worry about it when we were doing the task as human beings. But the theories that you have come up with will say something about how you're representing the task to yourself. So number of symbols might have been a feature that you looked at and used in your rule. Color is another feature that you might have used in your rule. And sometimes it really matters for a machine learning system what data we give it. So one thing you could do is you could just give the system bitmaps. That's going to make it really, really hard for it to learn. So for example, 150 by 60 pixel image for each example. And that gives you 9,000 values. So you're just giving it, basically you're giving it the pixels. The image has 9,000 pixels, so it has 9,000 features, and it has to figure out which ones are relevant and which ones are not. And it makes it very, very difficult for it to figure out the crucial things that we used when we categorize these things, like number of symbols, colors, and so on. At the very least, you probably have to do a whole bunch of image processing before you give it to it. Okay, a machine learner might be able to do well with this data eventually, but you're really tying its hands by doing that. So what could you do instead? Well, you could do like logical features like this. Like shape 1 is shape, color 1, shade 1. So if you think of each example, this is example 1, as having 3 shapes, 3 symbols, each of which has a shape, a color, and a shading. Shape, color, shading, shape, color, shading. And you put null when there isn't a symbol there. So this is example 1 is a green filled diamond and a purple filled diamond and nothing else. Example 2 is a red oval, an empty red oval, and has no other symbols, and so on. Example 6, that is, sorry. This makes the learning problem, this is only 9 features now instead of 9,000 features. So the system might be able to do something with that. It's going to take it a lot less time. It's going to be able to explore more options. And so on, but it still might find it quite difficult because the target rule talked about, the number of colors and the number of shapes and things like that. So you might want to put in higher order features, number of ovals, number of diamonds, number of colors. So you could expand this feature set by using these higher order features. And in a machine learning task, most of the time, different machine learning algorithms have different characteristics. Some of them cope really well with huge numbers of features. Some of them you need to simplify it, make fewer features. But in general, when you're starting out at least, you want to encode things with as many features as you can to give the learning system the best chance. All right, so that's task 1. I'm hoping you're kind of getting an idea for what's going on. The crucial lesson here is about overfitting. We need to abandon the idea that we want 100% accuracy. We want good accuracy, but not necessarily 100%. To be able to perform well on unseen tasks. Here's task number 2. These are the correct solutions. So again, this was the banknote authentication task. You have legal and counterfeit bills. This was the training data. Most people solve this by drawing lines or curves on here to try and mark out areas. I mean, it's pretty clear that there's a big area of green up here, a big area of red down here. So depending on how you drew your lines, you will have categorized, banknotes like these ones out here everyone will have the same categorization. In here, you might have different ones depending on how you've drawn your lines. This is what it's supposed to be. And you might look at this and cry foul because look at this, 2 points so close together, and one of them was counterfeit and one of them was legal. I'll say 2 things about that. One is this happens in real world data because of just random variance, because of maybe the machine didn't quite scan the image correctly. or because maybe the whole category is just really messy and you don't have the right features, you can often end up with two things that look very similar to the machine learning algorithm but have different categories attached to them. That can happen. In this particular data, if I had given you all four features, skewness, variance, entropy, and whatever the other one is, I can't remember, it's actually a solvable task, and you can get really good performance on it. So if you imagine a third dimension coming out of the screen, that might take all of the red points and put them over here and all the green points over here. So if you had a three-dimensional space, we're looking down into the three-dimensional space, you could cut it here and separate it. But it becomes really hard to visualize for human beings, especially when we add that fourth dimension. We don't know how to visualize things in 4 dimensions, so that's not going to help us very much. So in any case, I doubt anybody got 100% here. I'd be really surprised on the training or on the testing data. Now, there's just what I want to say about this is what I want to do is I want to use this to kind of preview some of the classifiers that we're going to look at. So you can think of a theory in a problem like this as a way to carve up a two-dimensional feature space or a multi-dimensional feature space. We're usually going to visualize these things in 2 dimensions, but the real algorithms are going to work on multiple dimensions. So for example, imagine drawing a line just down here. That would do, on its own, would do a pretty good job of separating things. Or imagine drawing a set of boxes around the pure points. We can often think of our learning algorithms as doing that, and we can classify our classifiers in depending on the type of the method that they use to split up the feature space. So simple neural networks and a technique called logistic regression, what they do is they try to categorize with a single straight line. So it learns the parameters of a line through a space like this and then categorizes everything on one side as, in this case, legal, and everything on the other side as counterfeit. So it might look like something like this. This theory gets 80% on the testing set. Okay? Data that this works well on is called linearly separable data. Text data is often linearly separable. So that's one type of theory. Here's another type of theory, rules or decision tree classifiers, which are kind of logically equivalent. So here is an example of a decision tree for classifying this space, these items. So V is variance and S is skewness. So we start at the top of the tree for every new example. So for example, let's take this example right here, this one. So it's got a variance of about 1 and a skewness of about, looks like about, let's call it 9. So variance 1, skewness 9. Okay, sorry about the cut there. I had my yes and no mixed up when I was going through the example. So yes is to the right, no is to the left. So is the variance, so we're classifying this point, is the variance less than negative 0.2? No, it's not. Is the skewness, so we're over on this side. Is the skewness greater than 4.5? Yes, it is. So we're up in here. So yes is to the right, and we come up with legal. Okay, so what a theory like this does is it breaks up a feature space into a set of boxes, and it also gets 80% accuracy. So it tries to make the boxes as pure as it possibly can. A decision tree learner, some of these boxes are pure, some of them are not. And when it can't, it can keep making boxes, or it can just stop and kind of give up, which is what it's done here. Okay, so there are errors in the training set, and many of the training set areas contain legal and counterfeit examples. That's done to avoid the problem of overfitting. Okay, and then there are other shapes, and these ones are a little bit harder to visualize, but other machine learning algorithms, so naive Bayes, deep neural networks, k-nearest neighbor, which we're going to look at, can be thought of as carving up they don't explicitly deal necessarily with drawing lines and boxes and things like that, but when you run them, you can model them as carving up the feature space in a much more nuanced way. So they can draw, in theory, they can end up drawing sort of unrestricted decision boundaries of any shape. So for example, a deep learning neural network might learn a boundary that looked like this. And again, it's getting about 80% accuracy here, but it's doing it with a different shaped decision boundary. which I think looks, I realized after I drew it, looks a bit like the Twitter bird, but it's not meant to. Okay, so just a quick summary, and I do encourage you to read this over. There's a bunch of terminology in here that we're going to be using over and over again. And there is a glossary of terminology in the resources section that you can take a look at if I use a term that you're not sure about. But we were looking at supervised classification, which is applying predefined labels to things that we haven't seen before. So we use training data, a set of data that's already been labeled, and we use that to we give that to the learning algorithm to form the theory. Each example consists of a list of values for a predefined set of features. So it might be, shape and shading and color of different items. It might be variance and skewness and kurtosis and entropy. The learning data uses those values, those numerical values usually, to form a model that tells it when to apply each label. And then we test it, see how well it's doing on the testing data. That's a set of examples that we held back. They've already been labeled, but we hold them back for ourselves and we don't give them to the algorithm. When it's done training, then we show it the testing data and see what it predicts and see how well it does. Okay? And when the features are numeric, like they were in our second task, we will often be graphing them. We'll be thinking about what's called the feature space. How do the examples cluster within the feature space, and how does our model carve out regions in the feature space? Okay, so that's a basic intro to the main task that we're going to look at starting next week. There's no exercises to do. I hope you did participate in at least one of these activities. And the next video we'll be back into Python, looking at how to read in data and how to create some scatter plots. These scatter plots, by the way, not the words on them and the boundaries, but these scatter plot graphs, the original banknote one and this one here, I should say this original banknote one and this one here, were created from Python. So I read in the data and created the scatter plots from Python. So I'll be showing you guys how to do that in the next video. See you then.